Science of Human Movement, Chapter 2. Science of Human Movement, Chapter 2. Learning objectives. Upon completion of this chapter, you will be able to identify key biomechanical terminology and topics in relation to integrated sports performance training. Explain functional anatomy as it relates to integrated sports performance. Define motor behavior in integrated sports performance. Page 20, Chapter 2, Part 1. I'm going to probably do 2 parts. Human movement science is the study of how the human movement system functions in an interdependent, interrelated scheme. The human movement system consists of muscular system, functional anatomy, articular system, functional biomechanics, and the neural system, motor behavior. Although they seem separate, each system and its components collaborate to form interdependent links. Although they seem separate, each system and its components collaborate to form interdependent links. In turn, this entire interdependent system must be responsive to internal and external environments while gathering necessary information to produce the appropriate movement patterns. This process ensures optimum functioning of the human movement system and optimum human movement in sports. It is important to review the pertinent aspects of each component of the human movement system as it relates to integrated sports performance training. Kinesiology, subheading Biomechanics. Kinesiology and biomechanics are 2 subdisciplines underneath the umbrella of human movement analysis. In Greek, kinesio means to move, and the term logi means to study. Similarly, bio means life, and mechanics is a physics term involving the study of how forces affect a living body. For example, the muscles exert an internal force in order to lift a heavy object off the ground. For example, the muscles exert an internal force in order to lift a heavy object off the ground. An external force includes a force that bodies. An external force includes the force of the body's weight as gravity pulls it down towards the Earth's center. At the same time, the ground also produces an external force called ground reaction force, felt at the feet when walking. In the ground reaction force, an equal and opposite force is exerted back onto the body with each step. Whether muscular, gravitational, or even bone-breaking forces affect the body depending on their magnitude, direction, and duration. Whether muscular, gravitational, or even bone-breaking forces affect the body depending on their magnitude, direction, and duration. When analyzing human motion, biomechanical analysis can be quantitative and qualitative. Quantitative analysis involves taking physical measurements and making mathematical computations to reach a conclusion. Today's specialized computer equipment can facilitate such computations, but require the knowledge and experience. Today's specialized computer equipment can facilitate such computations, but require the knowledge and experience of using such equipment. Qualitative analysis involves applying principles of proper technique and combining them with observations in order to make an educated evaluation. Ultimately, both types of analysis can help design a proper intervention for an athlete. The focus here will be largely on qualitative analysis. Anatomic terminology. All professions have language specific to their needs. The sports performance professional needs to understand the basic anatomical terminology for effective communication. Anatomic terminology. Planes of motion, axis, and combined joint motions. Human movement occurs in 3 dimensions. It is universally discussed in the system of planes and axes. 3 imaginary planes, sagittal, frontal, and transverse, are positioned through the body at right angles, so they intersect at the body center of mass. Movement is said to occur predominantly in a specific plane when movement occurs along or parallel to the plane. Though movements can be dominant in one plane, no motion occurs strictly in one plane of motion. Movement in a plane occurs around an axis running perpendicular to that plane, much like the axle around which a car wheel revolves. This is known as joint motion. Joint motions are termed for their action in each of the 3 planes of motion. The sagittal plane. Part 1. The sagittal plane bisects the body into right and left halves. Sagittal plane motion occurs around a frontal axis. Movements in the sagittal plane include flexion and extension. Flexion occurs when the relative angle between 2 adjacent segments decreases. Extension occurs when the relative angle between 2 adjacent segments increases. Flexion and extension occur in many joints in the body, including vertebrae, shoulder, elbow, wrist, hip, knee, foot, and hand. The ankle is unique in the sagittal plane. Flexion is more accurately termed dorsiflexion, and extension is referred to as plantar flexion. Examples of predominantly sagittal plane movements include bicep curls, tricep pushdowns, squats, front lunges, calf raises, walking, running, and climbing stairs. Sagittal plane. Closed down. Page 23. Page 24. Frontal plane. The frontal plane bisects the body into front and back halves, with frontal plane motion occurring around an anterior and posterior axis. Movements in the frontal plane include abduction and adduction of the limbs relative to the trunk, lateral flexion in the spine, and eversion and inversion of the foot and ankle complex. Abduction is a movement away from the midline of the body, or similar to extension and increase in the angle between 2 adjoining segments only in the frontal plane. Adduction is a movement of the segment toward the midline of the body, or, like flexion, a decrease in the angle between 2 adjoining segments only in the frontal plane. Only in the frontal plane. Lateral flexion is the bending of the spine, cervical, thoracic, and lumbar, from side to side, or simply side bending. Eversion and inversion relate to specifically to the movement of the calcaneus and tarsals in the frontal plane during functional movement of pronation and supination. Examples of frontal plane movement include side lateral raises, side lunges, and side shuffling. Page 25. Transverse plane. Transverse plane. The transverse plane bisects the body to create upper and lower halves. Transverse plane motion occurs around a longitudinal or vertical axis. Movements in the transverse plane include internal rotation and external rotation for the limbs, right and left rotation for the head and trunk and radial ulnar pronation, and supination, radial ulnar. The transverse plane motion of the foot is termed abduction, toes pointing outward, abduction, externally rotated, and adduction, toes pointing inward, internally rotated. Examples of transverse plane movement include cable rotation, turning lunges, throwing a ball, and swinging a bat. 26. During athletic movements, the body must maintain its center of gravity aligned over a constantly changing base of support. If a change in alignment occurs at one joint, changes in alignment of other joints must occur. For example, when an athlete stands and turns their patella inward, then outward, the obligatory effects from the subtalar joint to the pelvis are noticeable. When the patella is turned inward, the femoral internal rotation, total kinetic chain pronation, occurs at the subtalar joint, knee joint, and lumbo-pelvic hip complex, LPHC. When the patella is turned outward, femoral external rotation, total kinetic chain supination occurs. Even though a joint has a predominant plane of motion, all freely movable joints can display some movement in all three planes of motion. Functional multiplanar biomechanics can be simplified into pronation and supination. Functional multiplanar biomechanics can be simplified into pronation and supination. The key word being simplified. In reality, pronation is a multiplanar synchronized joint motion that occurs with eccentric muscle function. Thus, supination also is a multiplanar synchronized joint motion that occurs with a concentric muscle function. The gait cycle will be used to briefly describe functional biomechanics to show the interdependency of joint and muscle action on each other. During the initial contact phase of the gait, subtalar joint pronates, creates obligatory internal rotation of the, page 27, of the tibia, femur, and pelvis. In fact, during the initial contact phase of gait, the subtalar joint pronates, creating obligatory internal rotation of the tibia, femur, and pelvis. One more time. During the initial contact phase of gait, the subtalar joint pronates, creating obligatory internal rotation of the tibia, femur, and pelvis. Tibia, femur, and pelvis. At mid-stance, the subtalar joint supinates, leading to obligatory external rotation of the tibia, femur, pelvis. These linkages are bidirectional, e.g., example, pelvic motion can create lower extremity motion as well as vice versa. Poor control of pronation decreases the ability to eccentrically decelerate multi-segmental motion that can lead to muscle imbalances, joint dysfunction, and injury. Poor production of supination decreases the ability of the human movement system to concentrically produce the appropriate force for push-off that can lead to synergistic dominance. During functional movement patterns, almost every muscle has the same synergistic function. During functional movement patterns, almost every muscle has the same synergistic function. To essentially decelerate pronation or to concentrically accelerate supination. During functional movement patterns, almost every muscle has the same synergistic function. To eccentrically decelerate pronation or concentrically accelerate supination. When an articular structure is out of alignment, abnormal distorting forces are placed on the articular surfaces. Poor alignment also changes the mechanical function of muscle and force-coupled relationship of all the muscles that cross that joint. This leads to altered movement patterns, altered reciprocal inhibition, synergistic dominance, and ultimately decreased neuromuscular efficiency. In addition to three planes of motion, axis of motion. In addition to three planes of reference, there are also three axes of reference used to describe human movement. These axes are called medial, lateral, anterior, posterior, and longitudinal. Instead of an imaginary window pane that divides the body into halves, Each of these axes represents an imaginary line that passes through the body and is perpendicular to each plane with which it is associated. Specific movements rotate about each of the three axes, similar to the way a wheel on a bicycle rotates about its axis. The first to be discussed is the medial lateral axis. Medial lateral. In the sagittal plane, rotation happens around the medial lateral axis, also called the coronal axis. The medial lateral axis consists of an imaginary straight line that cuts through the body laterally from side to side. The medial lateral axis consists of an imaginary straight line that cuts through the body laterally, side to side. This can be thought of as a long pin that crosses the neck from one side of the shoulder to the other. Nodding the head forward and backward is a movement that occurs around a medial lateral axis. An axis is perpendicular to its plane. A joint moving in the sagittal plane will rotate about an axis that runs from side to side. A joint moving in the sagittal plane will rotate about an axis that runs from side to side. Another example, raising and bending the knee joint, as occurs during running, is another sagittal plane movement that also happens about a medial lateral axis. The anterior-posterior axis consists of a straight line that cuts through the body from front to back. This can be thought of as a long pin crossing the shoulder joint from front to back, anterior, posterior. Rotation of the shoulder joint will occur around that axis. For example, raising the arm laterally is a frontal plane movement that happens around an anterior-posterior axis. Frontal plane movements are sideways, so the frontal plane axis will be an imaginary line that runs from front to back of the body. During a frontal plane movement, such as jumping jacks, an anterior-posterior axis runs through each shoulder and hip. Lastly, there is a longitudinal axis where an imaginary long and straight line cuts through the body from top to bottom. An imaginary plumb line that hangs from the head and runs downward to where the feet are can also be thought of when referring to the longitudinal axis. An imaginary plumb line that hangs from the head and runs downward to where the feet are can also be thought of when referring to the longitudinal axis. Rotation around a longitudinal axis takes place in the transverse plane. Spinal rotation with twisting of the trunk is an example of the rotation about a longitudinal axis. Page 28, Chapter 2, Part 1. Muscle actions. Muscle produce tension through a variety of means to effectively manipulate gravity, ground reaction force, momentum, and external resistance. There are three different muscle actions: eccentric, isometric, concentric. An eccentric contraction occurs when a muscle develops tension while lengthening. The muscle lengthens because the contractile force is less than the resistive forces. The overall tension within the muscle is less than the external forces trying to lengthen the muscle. During resistance training, an eccentric muscle action is also known as a negative. This occurs during the lowering phase of any resistance exercise. During integrated resistance training, the eccentric action exerted by the muscles prevents the weight, resistance, or implement from accelerating downward to the gravitational due to gravitational forces. During integrated resistance training, the eccentric action exerted by the muscles prevents weight, resistance, or implement from accelerating downward due to gravitational forces. In athletic activities, muscle work as much eccentrically as concentrically or isometrically. Eccentrically, the muscle must decelerate or reduce the forces acting on the body, or force reduction. This is a critical aspect of all forms of athletic movement because the weight of the body must decelerate and then be stabilized. Eccentrically, the muscle must decelerate or reduce the forces acting on the body, or force reduction. This is a critical aspect of all forms of athletic movement because the weight of the body must be decelerated and then stabilized in order to properly accelerate during sprinting, cutting, or jumping. Isometric. An isometric muscle action occurs when the contractile force is equal to the resistant force, leading to no visible change in the muscle length. As the muscle shortens, elastic components of the muscle lengthen. The muscle is shortening, however, there is no movement of the joint. In athletic activities, isometric actions dynamically stabilize the body. This can be seen when stabilizers isometrically contract to restrict a limb from moving in an unwanted direction. For example, when cutting, the adductors and abductors will dynamically stabilize the leg from excessive movements in the frontal and transverse planes. During jumping, the transverse abdominis and multifidus, page 29, transverse abdominis and multifidus muscles stabilize the lumbar spine. During throwing, the rotator cuff dynamically stabilizes the shoulder joint. During throwing, the rotator cuff dynamically stabilizes the shoulder joint. A concentric muscle action occurs when the contractile force is greater than resistant force, resulting in a shortening of muscles in visible joint movement. This is referred to as the positive during integrated resistance training. In athletic activities, all explosive movements require concentric muscle actions including sprinting, jumping, cutting, and throwing. Subheading muscular force. A force is defined as the interaction between two entities or bodies that result in either the acceleration or deceleration of an object. Forces are characterized, page 30, by both magnitude, how strong, and direction, which way they are moving. The human movement system manipulates variable forces from a multitude of directions to effectively produce movement. As such, the sports performance professional must gain an understanding of some of the more pertinent mechanical factors that affect force development that the human movement system must deal with, and how motion is affected. How are these not run-on sentences? The amount of force produced is dependent on an object's mass multiplied by how fast it is moving. The following equation can assist in the visualization of this concept. The following equation can assist in the visualization of this concept. Force equals mass times acceleration. Force equals mass times acceleration. Where mass is the amount of matter in an object, and acceleration is how fast the object is moving. When a substance takes up space, it can be regarded as matter. When a muscle with relatively large amount of mass moves very quickly, it will most likely apply a larger amount of force. When a substance takes up space, it can be regarded as matter. When a muscle with a relatively large amount of mass moves very quickly, it will most likely apply a larger amount of force. It is important to note that mass is different from weight. Weight is a force, and it is the amount of force that gravity has on the body. Weight is a force, and it is the amount of force that gravity has on the body, or that body. Weight is measured in pounds. Gravity is yet another force. It accelerates downward toward the Earth's center. Forces can be internal, such as produced by muscle, Forces can be internal, such as those produced by muscles to move limbs, or they can be external, such as those of mass, weight, and gravity. It is possible to manipulate these external forces to challenge athletes during exercise program. For example, mass can be added in the form of a barbell, dumbbell, or kettlebell during an exercise such as a squat or lunge. Some exercises can simply be body weight exercises. These challenge the athlete thanks to the pull of gravity. Exercises such as push-ups, squats, lunges, and jumping jacks are all body weight exercises that can be performed without external weight. Suspension body weight training is another alternative that manipulates body weight and gravity to challenge the athlete during exercise. Movements such as push-ups, rows, squats, and lunges can be performed while using a suspension body weight training. Length tension relationships. Length tension relationships. Length tension relationships refers to the resting length of a muscle and the tension the muscle can produce at this resting length. There is an optimal muscle length where the actin and myosin filaments in the sarcomere have the greatest degree of overlap. The thick myosin filament is able to make the maximal amount of connections with active sites on the thin actin filament, leading to maximal tension development of that muscle. When the muscle is stimulated at lengths greater than or less than this optimal length, the resulting tension is less because there are fewer interactions of myosin cross bridges and active sites. When the muscle is stimulated at lengths greater than or less than this optimal length, the resulting tension is less because there are fewer interactions of the myosin cross bridges and actin sites. This concept is important to the sports performance professional and coincides with the previously discussed concept of joint alignment. The starting point for a lift, the proper posture, the ability or inability to develop tension when reacting or correcting a movement are all affected by the length of the muscle when stimulated. Just as the position of one joint can drastically affect other joints, a change in joint angle can affect the tension produced by muscles that surround the joint. If muscle length is altered as a result of misalignment or posture, tension development will be reduced and the muscle will be unable to generate proper force for efficient movement. Page 20, page 31. With movement at one joint being interdependent on movement or preparation for movement of other joints, any dysfunction in the chain of events producing movement will have direct effects elsewhere. With movement at one joint being interdependent on movement or preparation for movement of other joints, any dysfunction in the chain of events producing movement will have direct effects elsewhere. Force velocity curve. Force velocity curve. Force velocity curve refers to the relationship of muscles' ability to produce tension at different shortening cycles. This is a hyperbolic relationship. This hyperbolic relationship shows that as the velocity of a concentric contraction increases, the developed tension decreases. This hyperbolic relationship shows that as the velocity of a concentric contraction increases, the developed tension decreases. The velocity of shortening appears to be related to the maximum rate at which the cross bridges can cycle. You guys are horrible. This is how it's written. The velocity of shortening appears to be related to the maximum rate at which the cross bridges can cycle can be influenced by the external load. No, that cannot be right. The velocity of shortening appears to be related to the maximum rate at which the cross bridges can cycle and then be influenced by the external load and can be influenced by the external load. Conversely, with eccentric muscle action, as the velocity of the muscle action increases, the ability to develop force increases. Conversely, with eccentric muscle action, as the velocity of muscle action increases, the ability to develop force increases. This is believed to be the result of the use of elastic component of the connective tissue surrounding and within the muscle. Muscles produce a force transmitted to bones through elastic connective tissue tendons. Muscles produce a force transmitted to bones through elastic and connective tissues that are tendons. Because muscles are recruited as groups, many muscles will transmit force onto their respective bones, creating movement at the joints. This synergistic action of muscle to produce movement around a joint is also known as force couple. Muscles in a force couple provide divergent tension to the bone or bones to which they attach. Because each muscle has different attachment sites in lever systems, the tension at different angles create a different force on that joint. The motion that results from these forces is dependent upon the structure of the joint, intrinsic properties of each fiber, and the collective pull of each muscle involved. In reality, however, every movement a person produces must involve all muscle actions, eccentric, isometric, concentric, and functions, agonists, synergists, stabilizers, antagonists, to ensure proper joint motion as well as minimize unwanted motion. Therefore, all muscles work together for the production of proper movement are working in a force-couple relationship. Proper force-couple relationships are needed so the human movement system moves in a desired manner. This can only happen if the muscles are at the optimal length tension relationships. Excuse me. This can only happen if the muscles are at the optimal length tension relationships and the joints have proper arthrokinematics or joint motion. Collectively, optimal length tension relationship, force couple relationship, and arthrokinematics produce ideal sensory motor integration and ultimately proper efficient movement. The amount of muscular leverage in arthrokinematics. This is a huge one. Muscular leverage in arthrokinematics. The amount of force the human movement system can produce is not only dependent upon motor unit and muscle side, but also on the lever system of the joint. A lever system is composed of some force, muscles, a resistance, load to be moved, lever arms, bones, and fulcrum, the pivot point. Three classes of levers are present in the body. A class 1 lever has the fulcrum between the force and the load. The force and the load, class 1. A class 2 lever system. A class 2 lever has the load between the force and the fulcrum. Class 1. A class 2 lever has the load between the force and the fulcrum. Class 3 levers, the most common in the body, have the pull between the load and the fulcrum. Class 1, teeter-totter, flexion, extension of the head. Body exam. Class 2, wheelbarrow, dorsiflexion, rising up on the toes. That's class 2. Class 3, lifting a shovel, forearm flexion. In the human movement system, the bones act as lever arms that move a load from the force applied by the muscles. This movement around an axis can be termed rotary motion and implies that the levers, bones, which are the bones, rotate around the axis joints. This turning effect of the joint is often referred to as torque. In resistance training, torque, distance from the load to the center of the axis of rotation times the force, is applied so joints can move. Since the neuromuscular system is ultimately responsible for manipulating force, the amount of leverage the human movement system will have for any given movement depends on the leverage of the muscle in relation to the resistance. The difference between the distance the weight is from the center of the joint and the muscle's attachment is from the joint. God damn, these guys, they don't know how to write. The difference between the distance the weight is from the center of the joint and the muscle's attachment is from the joint will determine the efficiency with which the muscle manipulate the movement. One more time. The difference between the distance the weight is from the center of the joint and the muscle's attachment is from the joint will determine the efficiency with which the muscles manipulate the movement. I have no idea what that is. Since attachment sites and line of pull of muscle through the tendon can be altered, the easiest way to alter oh my God. Since attachment sites and line of pull muscle through the tendon cannot be altered, the easiest way to alter the amount of torque generated at the force is to move the resistance. In other words, the closer the weight is to the point of rotation, the joint, the less torque it creates. In other words, the closer the weight is to the point of rotation, the joint, the less torque it creates. The farther away the weight is from the joint, from the point of rotation, the more torque it creates. For example, to hold a dumbbell straight out, side arm's length, shoulder abduction. The weight may be approximately 24 inches from the center of the shoulder. Shoulder joint. The prime mover for the shoulder abduction is the deltoid muscle. its attachment would be approximately 2 inches from its attachment would be approximately 2 inches from the joint center. That is disparity of 22 inches, or roughly 12 times the difference. I have no idea what this means. If the weight is moved closer to the joint center, for example to the elbow, the resistance is only approximately 12 inches from the joint center. Now the difference is only 10 inches, or 5 times greater. Essentially, the torque required to hold the weight was reduced by half. Many people performing side lateral raises with dumbbells, laterally raising dumbbells to the side, do this inadvertently by flexing their elbow, bringing the weight closer to the shoulder and effectively reducing the required torque. Sports performance professionals can use the principle as a regression for exercise that are too demanding, reducing the torque placed on the human movement system, or as a progression to increase the torque and place greater demand on the human movement system. Functional anatomy. Functional anatomy.